All right, good morning. I'm Eric Ziegast. I'm honored to be here. Thanks for having me. I come from Farsight Security. We are a spinoff or offshoot of Internet Systems Consortium, the people who brought you Bind. But we've had a focus on security technologies and making data available for the security industry. So all those products that you have, from antivirus to intrusion detection systems and law enforcement, et cetera, a lot of the people use the data that we make available. A lot of our products are based around DNS monitoring. Company was founded by Paul Vixie. I've worked for him for about 8 or 9 years now. So today we're going to be talking about DNS technologies for resiliency. It's my showcasing 3 technologies which have not been presented at MENOG yet, but and also have some information regarding previous presentations, and you may be able to go through some of the notes and use that as a guide to help you with your own introduction to these technologies. So today I'm going to be reviewing 2 past presentations that were given at MENOG. I recommend that they be looked at. The first one was the practical DNS operations. It was a great tutorial by John Christoph with Team Cumry at the time. Went through all sorts of parts about how to run operations, or tips and tricks for someone who needs the operational help for how common problems that you would have, common things that you need to know about serving your DNS, both for authoritative but also for recursive as well. Went through the hierarchical structure of DNS. I'm actually going to go over that again today. Differences between what a registry and a registrar is, who is, how recursion works, how delegation works, how not to block your users from DNS by firewalling TCP, best common practices for running name servers, including having multiple name servers, load balancing between name servers, using load balancers, deploying Anycast, making sure that you have diverse networks to your name servers. Talking about things on your network which don't go right. So for example, open resolvers have been a large problem in the past. Talk about cache poisoning. There are many parts to his presentation, and it's well worth reviewing. Again, I'm not going to go into that today. Another part which I think is very, very well worth reviewing, operator or authoritative, is DNS Anycast. There were 2 great presentations given at MENOG. I've listed them here with links to those presentations. And I also add another blog series that I found, which actually goes through each of the different parts, whether it's Anycast, how the technology works, and how to deploy it on routers for the various different types. And if you don't use Anycast, I think this is going to be one of the best places to start as you set up your own lab. The part that it may not be covered is making sure that your name server can bring itself into or out of an Anycast cloud based on what it thinks its own ability to serve DNS is. Because it doesn't make sense to have a name server that doesn't work be part of your Anycast cloud. But if you can pull your route down, it works as well as any global service load balancer that you can find. And it's not just, this technology is not just for authoritative servers. Many people know that this is already used by the DNS root operators, as well as many of the CCTLD and GTLD operators. But because DNS is so critical to operations, it will impact your service if you still list and provide via DHCP one name server or another name server. While a server can go down, the failover that you would have in your client stub resolver is too long that you're basically going to get phone calls from your users. Hey, why is the internet down? When it may be just a DNS issue. Anycast automatically takes advantage of several failure modes, whereas if you can get to the IP address for the name server, if the single name server goes down, if an entire node for your name servers goes down, you have other nodes set up in other locations, the DNS will still continue to work in the most efficient way possible for your network. So if you're a recursive service operator on behalf of your customer populations, it's well worth looking at deploying Anycast for your recursive servers. There are many enhanced and public DNS providers that use the service. For example, OpenDNS, Google, and others. There are security companies that are now pointing people into their Anycast clouds for how to provide an enhanced DNS service, which may be above and beyond what their local DNS or their local internet service provider or hotel or airport Wi-Fi might be providing for them. So if you have a large user base, I wholeheartedly recommend that you look into DNS Anycast. A problem that many are facing today is DDoS. And one of the most common targets might be websites, but DNS is also targeted as well because it is a linchpin for people being able to access or it's a gatekeeper for people being able to access services. If you can take down the DNS, not all the DNS because criminals need the DNS too to do what they need to, but specific DNS, then it is disruptive and the criminals win. Many root operators, not all of them, but most of them deploy Anycast. There is diversity in how the root operators run their operations. They use different name service platforms, different architectures, different switches and routers in how they operate their services, but many of them do deploy Anycast. One reason is to have more global bandwidth available for all of the services. It makes more bit in one location. It localizes DDoS attacks. When one node goes down, so for example, if a country's IP infrastructure is being taken down, if there happens to be a root node in that country, then if it's an external attack, then people are still able to use parts of the DNS from within the country. And if it's attacks coming from within the country, the global service for providing DNS is not as impacted, just localized to the country where the traffic is coming from. And there's also reduced latency from operating name servers close to the end users. So that is one of the reasons why many operators deploy Anycast. The DNS software and for DNS software and architecture diversity, as I've said before, that many operators, they don't all run the same software. A vulnerability or issue that happens with one set of software may not affect all the other pieces of other software at the same time. Someone who may have started with bind may now use bind and NSD for authoritative now, or they may write their own custom software or deploy Power DNS for some, for custom database or registry solutions. They also have different management practices as well. It's the operators of name servers. They are in different countries and jurisdictions. There's a shared fate of the internet over what might be happening for any particular country or any particular company's self-interest. If you don't have your own root server on your network, you may investigate that. There was a presentation also at at RIPE that talks about the benefits of having a root server inside of your country. So it's well worth looking at. You will provide better service for your customers as an access operator, and it will also help you in the event of network issues beyond your provider. For CCTLD and GTLD operators, many top-level domains, they may only have a few name servers that are serving the domain. That method is no longer resilient for attacks. Some have gone out to say, hey, you're run on a different network. You can provide a secondary for me. That's no longer good enough. Several services have sprouted up since 2009. That provide Anycast DNS services. For example, PCH, one of our sponsors, ISC, Newstar, Akamai, Many of them provide services, some of them for free for public benefit. If you have, let's say, up to 6 records for your ccTLD or gTLD, you might use a mix of providers because one of those providers may actually be under attack. It would make sense for you to actually have some of your own servers to deploy your own name service, maybe as a stealth master. So you basically only have your secondaries facing the world while your administration of the domain is still protected behind your network borders. And you might also look for DDoS mitigation services where you do serve your own DNS servers. For end users, there are many DNS services out there that you can buy or secondary from the previous providers or a bunch of others. For example, I think Cloudflare is attending here. They have Anti-DDoS and Google Shield. There are several services out there that you can use as well. And many of the banks have figured out how to use different DDoS providers commercially. There are 3 technologies I'd like to go over today. One of which is called response policy zones. It is a technology that will help allow you to mitigate threats faster than it would be through the old takedown methods. Another technology is response rate limiting, which has been implemented to help mitigate some of the effects of DDoS attacks on authoritative name servers. I'll also talk about recursor rate limiting as well. And then the last thing I'm going to be talking as far as the technology is a new logging technology called DNSTAP. So I believe it was back in 2008 or 2009, Paul Vixie wrote an article on Circle ID called Taking Back the DNS. It was when he released the technology as a patch for bind. And there was frustration at how takedowns for domains have not been scalable. The bad guys have learned how to register domains on the cheap, and it's asymmetric warfare. Their ability to be robust and act nimbly through all the infrastructure is far faster than the infrastructure of the security industry and the registries and registrars to be able to mitigate attacks, or law enforcement to go after some of the bad guys. In order to protect your class of service, he created a industry-neutral technology where you can, in a zone file, provide alternative answers for any set of global identifiers that you want, whether they be domain names, host names, based on answers pointing to a particular IP address, or domains that use a particular name server that is used for something that you don't want. It also has built in some technology for whitelisting and other things to help with your own operations. The cleanup of domain abuse is time consuming. Just about everything with criminal campaigns today is automated, from the registration process to how they do hosting. It's a matter of just having credit cards on file, and they just keep going. The mitigation is expensive due to cost shifting. Some ISPs or registrars or registries may be less responsive than others. And that the detriment is that bad services are left online and not taken down. It's not until you have, say, Google Safe Browsing or antivirus or something will come out to update that you'll actually be blocked from that in a traditional sense. With RPZ, if you are able to use services where you are provided, these lists of threats of bad domains or bad indicators, it will actually reduce the speed at which, or it will increase your ability to more quickly respond to those threats. And in some cases, some things can't be taken down. There are bulletproof hosting providers. Some registries might have policies that will not allow you to take down their domains unless you get, say, a local court order, which is perhaps difficult, or many would just give up. Good thing is that criminals tend to reuse a lot of the same infrastructure. While the domain system is relatively disposable, they still need infrastructure, stolen servers, stolen computers. When I say stolen, meaning there's malware running on them or they've been hacked into, or they actually have to buy as glue for their networks, they still have to buy or host access in relative areas. In many cases, there will be what's called bulletproof hosting, where legally it's hard for law enforcement to go after them because, well, many reasons. And something else which some may not think about, but not all crime is equal. Crime in one region may be different from a crime in another. If RPZ could actually give an ISP or even a country more flexibility about how to reduce the ability of their users to visit other websites. And based on what your local policy, you don't necessarily have to go to the remote country to say, I need to take you down. Say, oh, that's not illegal here. And so it doesn't get taken down. But now you can actually, through DNS, have a way to firewall access to certain identifiers on the internet. This is an example of just new domains being registered every day. Just about an hour before here, I'm just going through and looking at here are all the new domains that are being seen for the first time that start with a number. A product of this called newly observed domains, which can be put into a DNS firewall that says, if for the first day, don't have anyone visit any of these domains because all of the big content providers and all the people who want to serve content on the internet, they've probably created a sensible name to be visible everywhere. Whereas many of the drive-by-night, fly-by-night criminals will register a domain, use the domain in spam campaigns, malvertising, and for whatever other purposes they have, and then unregister the domain all within the same day. So even if you download zone files from the registries, you may not see any of these domains. Paul Vixia stood on stage and said, most new domain names are crap. And so that is one example of that. Some domain names you may not realize are bad until it's too late. Just last week, someone blogged an article about how that domain there, which uses Unicode, can actually look like a real domain name. You wouldn't be able to tell it from your URL bar, but it is actually a different domain, and it may serve something else. People who are doing phishing, like against banks or other institutions, even government, they may take advantage of this to lure people to content which looks correct but is not. With RPZ, you can actually prevent people from accessing that content even if you're not able to take it down. For the notification of bad content, having a dynamic near real-time distribution method is desirable, something that is industry neutral, and out of that has sprouted several providers, some of which you may be aware of, like Serval, Spam House, our company, ThreatStop, Internet Identity. They've all created response policy zones to say, these are the threats that we think people should stay away from. And people are able to automatically incorporate them not only into their end user open source DNS software, but also in the products. There are product vendors who use the technology inside of their products and can actually take the feeds in. And when they're distributed, they are distributed in real time. You do an update, you do like a dynamic DNS update, goes through incremental zone transfers, and it's actually at the endpoint being enforced within 5 seconds of publishing. That's not something that you can do with, say, downloading files and manually editing your own zone files. Previous methods that people have used to do this is to create their own root zone with all the bad names that they don't want people to go to, and that would be manually administered. You'd have to reload your name server, reload the zone. This is something where it goes from a provider whose primary job is to detect into your system. Proprietary software is also available from some of the more commercial DNS providers. But this is, RPZ is an open platform and ecosystem for making this available. There are no patents or licenses for it. These were some of the design goals that we had for when we actually created this technology. I'm not going to go into that. For the DNS hierarchy, and before explaining how it works, I'm going to give a little bit of a background of how the DNS works, so you can understand how specifically RPZ works as opposed to normal DNS. So I hope many of you are familiar with what a DNS hierarchy looks like. We have root name servers, gTLD and ccTLD name servers, and there are different hierarchies where part of the domain database is delegated out to different providers at different levels. You might have a provider that is listed in multiple parts of the space at different places. For example, omontel.com.om, omontel.om, omontel.net.om. They might be for different things. And by the way, quickly, thanks to our sponsors, we wouldn't be here and so comfortable if it weren't for them. So I put them in as a slide for the examples. For normal DNS, I'm going to go through that briefly so you can understand each part of the transaction. So in here I have showed at the bottom is just a typical computer. It would be someone's iPad or someone's laptop or a server that needs to utilize the DNS to do what it needs to do. Provided by the DNS, provided in DHCP or manually configured, there will be a caching recursive DNS server. Some might call it a recursive server, some might call it a recursor. But it is the server that is going to fulfill requests on behalf of any client on the network, typically the local network. If you're a global recursive name service provider, people would manually configure your service to point the requests at your server. There is a protocol below and above the recursor. I'll get into that in a bit. But the first thing that the recursive DNS server is going to do when it doesn't have any information is it's going to go up through the DNS hierarchy, starting at the root and find its way down to the content that it needs to get to, or the information that it needs to get to. So it will pass, hey, I'd like to visit malwareinfected.com. Let's say that there was a payload dropped on our client. And the root server would say, well, I don't know, but go ask the com name server. So it will go ahead and refer the recursive name server to the delegated name server for the gTLD. So there are two protocols. One's below the recursive and one's above the recursive. The recursive server is acting on behalf of all the clients to make sure that it can resolve the name through the entire tree on behalf of the client. The next thing that the recursive name server is recursively go through the tree, and in this case, it'll ask the same question to one of the .com servers run by VeriSign. And it'll ask the same question. In this case, it'll get a different answer that says, well, I don't know the answer, but go ahead and ask the authoritative name server I have registered for that domain. And finally, it will ask the registered name server, or one of the registered name servers, and it'll actually get an answer back, not an NS record. It'll have additional information like name servers, IP addresses for those name servers, but it will actually take that answer. It will put it in its local cache so that if the next person comes by and asks, it will actually immediately, for a certain amount of time, make that answer available and efficiently. And that's how the DNS is made scalable. The answer is finally brought back to the client device, and all that work behind the scenes is done on behalf of the recursive server. There's monitoring at different levels. I'll actually go into that when I talk about DNSTAP. But what I'm going to go into here is RPZ would actually help prevent the bad information to get back to a user. In this case, it was a test domain to actually show you how it works, and and in this case, the end client would have been infected. It's a generic term is DNS firewall. It uses the same technology for secondary domains, zone transfers, incremental zone transfers, notifies for updates. You can treat it like a zone, so you can use dynamic updates, and you can list multiple response policy zones within a server. I'm short on time, so I'm actually going to skip through this a little bit faster. I will be available for the rest of the day if people would actually like to go deeper in depth. There can be multiple service providers. So as I said, there are several commercial providers. You can also maintain your own block list if you do your own investigations or abuse mitigation. You can actually provide censorship for your own users. And you can actually provide whitelists to make sure other people's lists won't interfere with your operations. Here's an example here of one of the configuration lines. It's relatively simple within Bind. Other providers are making pieces of RPZ available. I believe Not is, and there are actually pieces of this technology being added to Microsoft DNS Server as well. You can read the draft, which is very specific about the different actions. There are multiple actions you can take. It's not just a particular name that you can modify to say, hey, for a particular name, don't give an answer or say the domain does not exist. Don't send any data. Don't respond to a client. To rewrite it to something else, you can use RPZ to point a web request to your own logging web server, and then you can actually gather the refer in your web logs for something that would have directed to someplace else. So you can actually see why someone why it was actually part of the policy. You can also use triggers based on the answer, the IP address. If you know that a particular network block is bad or a particular IP address block is bad, you can list just the IP address, and every DNS name that points to that DNS will be dropped, or your action will be applied to redirect them, say NX domain or whatever. You can also have a trigger for by particular name servers, and this is useful if you know that a particular name server is bad. The distribution method would actually start from a single policy, and in this case, when you do the lookup again, when the response policy zone is implemented on the recursive caching name server, it will get instead an NX domain. So instead of going to a website, this is a demo web page, this is what someone would see instead if they're given an NX domain response. Even though it is still being served out there, it is no longer seen. And if you need to do debugging, you can use dig and can actually see things in the SOA records that would actually point people to say, oh, it was modified. Distribution is relatively scalable, and it's a great technology. If I could have 5 more minutes, I'd like to go into ORL and DNSTAP. Is that okay? Great. So response rate limiting, basically, it is actually implemented in just about all of the major servers now. So if you aren't familiar with response rate limiting and you run Authoritative for running your name server now, there are links here for all the major ones. Essentially, a reflective distributed denial of service attack is a particular client, whether it's someone's home router or something else that was infected, is going to send all repetitive requests looking to a particular authoritative name server. And the large answer is because the source address is spoofed, because BCP 38, BCP 84 is not universally implemented, all the answers will go back to the forged target address. And that is what helps take down the large providers. What response rate limiting does is it actually reduces the responses using DNS as a context for rate limiting to, after only a few of the first queries, to start dropping responses. So Ed Winstead from ISC, he provided these slides for me. Before it was actually deployed, they were actually getting lots of traffic to their root servers. After they deployed it, it smoothed everything out, and all of that extra traffic, which was attack traffic, just fell off. And at some point in the future, the attackers actually gave up. They moved on to some other target, some other domain that wasn't implementing response rate limiting. A friend of mine that works at Affilius, when he implemented there, he saw a huge drop when people were not able to use ripe.net anymore. There are many advantages of them. You can read the slide for them. There are common configurations methods for that as well. It's basically, the generic is, how many responses are you allowing in a certain time rate? And it will start dropping or modifying requests to force resolvers to use TCP connections for real requests, while the bad guys won't try that. And it's very effective for that part of mitigation. There's also, for anyone who operates a recursive server, there's something called recursive rate limiting. Some of the name servers out there will actually, there are certain types of attacks which are hard to defend against if they're using your resources for that. And in this case, let's say for a Mirai botnet or something else that's out there, you can use a random string.domain to saturate the request going to an authoritative name server. To help mitigate those attacks coming from your network, it is well worth looking at the variables inside of your name server that could help mitigate that. Because when someone calls you to say, hey, you're attacking my network, this is one way from your recursive servers to mitigate that. DNSTAP was created to provide a industry-wide logging mechanism efficient in most of the servers on the internet. Designed by Robert Edmonds, who worked with us. Some of my slides are also courtesy of Jeroen Massar, who presented at APWG. Again, we have the below recursive and above recursive lookups. There are different terminology here. Stub resolver is what's used on the clients. Caching recursive server we've already gone into, and authoritative name servers we've already gone into. The applications actually use a function to access the stub resolver and even have their own caches on those servers now, Linux boxes, Mac OS, etc. Here's a simplified view of that diagram, and there are different types of logging that people do. It might be query logging, where you're actually logging the queries to your authoritative name server. Passive DNS replication, which our company specializes in, but others as well. In fact, there are even efforts all over the world where people are gathering this data. And query logging used by intrusion detection systems. There are many ways of doing this on the network, but they are not efficient. And one of the best parts about DNSTAP is it's implemented in the name servers, so therefore you have more context about how and why the DNS name is being looked up and what the response means, as opposed to trying to recombine that together based out of network behavior. The system logging within most of the name servers is abysmal. It blocks on various parts of the kernel and is not usable for monitoring. There are different places where you can monitor DNS. I'm going to go back to that slide later. I'm not going to go into them. There are different places in this structure where in the software the hooks are there to monitor at a particular level. For passive DNS, it would be a combination of request query and request response. For an IDS system, might be looking at client query and client response, or the stub query and stub response at various places. There's an asymmetric method for passing the data within a multi-threaded environment in the name servers inside of the name servers out to a Unix socket. Outside of the name server, another process can attach to that socket to read all the data as a binary byte stream. The entire contents of the DNS messages are actually inside the messages. The messages are Google protocol buffers. Developers would have relatively easy data, much like TCP dump. and you can read the data as well. Provided by bind, DNSTAP read will help go through a whole bunch of names. As far as performance, this is, Jeroen did a baseline of performance of how, in the red here, the logging falls over. The logging falls over for bind and unbound. But for DNSTAP, the amount of additional processing is relatively negligible, and it keeps up with the name server as it increases in performance. A recent performance test we've done showed that DNSTAP is less than 1% of the system CPU resources on a name server, whereas TCP dump might consume 10% or more when a server is heavily loaded. So we're going to actually have Medica KO present at DNS OARC. Anyone who's interested in this should actually look for her presentation coming up in another week or two. Another thing to just keep in note is that there's a new technology out there called dprive, which is going to start encrypting between the stub resolvers and recursive servers. Many IDS systems, many ISPs may not be able to monitor DNS in the future. And so learning how to use monitoring at the recursive name server level is going to be very useful for people researching incidents and creating security products. Thank you. Sorry, it was very, very loaded with content. I will be here for questions all afternoon during lunch, so if you want demos or anything, let me know.
Thank you, Eric.